Let's go. So, hello. Today I would like to speak about an AC network. Previous time we solved a DC network. Now let's take an alternating current. I have prepared a small experiment. I have source 100 volt AC source, transformer. I have put switch here. 1 ampere meter will measure total current. I have one branch with independence and one, another branch with another method, and I will have ability to switch between lamp and condenser block. And this connects together. Very simple experiment. Here it is. So here is the meter 1. Measuring sum of currents. This one will measure current 2 and maybe I should switch them. It will be better. So this measures now second current and this one first current. Let's see what happens. Voltage arrived. What do we see? Current number 1 0.8 ohms, current number 2 0.8 ohms, and summary current 1.572, very close to 1.6. There is a big difference. Minus it's 0.79. So what I'm doing in general, I'm checking the first Kirchhoff law, Kirchhoff current law. For this node, sum of current should be 0. And look like it will be. Now let's see what happens when I switch from the lamp to condenser. Upon 0, upon 0.4, but sum of them should be 1.6, but we see only 1.14. We'll come closer. Can you see it? Two amps. Sum of current. .57. No 0.8 plus 0.8 should be 1.6, and we see 1.57. I'm switching to condenser, and we see 0.8, 0.8, but sum is only 1.14. With the lamp, with the condenser. We see problem here, isn't it? What's going on? Should we say what first Kirchhoff law, Kirchhoff current law is violated? Something wrong here. Let's bring in scope. Two lamps. I have go a bit closer. This. You can see three traces. Yellow, green, and say violet. Three traces. The first one is voltage. .100 actual 99.4. And I have two currents. Maybe I should reposition them. I have switched off the first lamp. It is two lamps, two currents. You can see currents are equal. Now condenser is in. You see this current? Maybe to make them more. Oh, 1 second. Look at that. 1 second. I have power. What's going on now? 2 amps. Oh. Now I have condenser. And you can see the difference. Can you see it? With the lamp, the currents are equal. With the condenser, see the shift. If you take Kirchhoff's law for instant values, everything should be okay. If you have a second, I'll bring the sum of currents to the screen. I just need to put a current sensor in. I have one free channel, and where is it? So this will outflow. One moment, I'm just. Speed. And here it is, the sum of currents. Lamp or resistive load, condenser, so we can say, but in instant values, looks okay. It disturbed, but it's not a problem in general. But we definitely have problem with the measurements. You see, sum of 0.8 or 0.8 is not equal to 1.4. hope shows something. Let's see, something strange. Do you see angular difference in some current and voltage? Two poles. Everything seems fine. Both in condenser we see angular shift. While values on the meter is it. So what's the problem? Why such thing happens? We have an element in our network, condenser, able to store energy. The element able to store energy. Network with condenser, current, schematic, is a voltage. What can I use? I can use a kind of water analogue. Maybe you remember. Yeah, say water flows. The difference of level is a voltage, amount of water is a current, and let's say cross section of the pipe is resistance. Simple analogy to the Ohm law. For condenser, I can go ahead with water analogy. Let's say we have some reservoir, water flows in. What will be? The level of the water. It's some analogy of condenser voltage. It will, what it depends, it will be all water in flow, but we also with the different tanks, we will see the different rise of level. Sum of all water divided by something corresponding to the let's say volume of our vessel. Here I can write what? Condenser voltage is 1 divided by capacity. It's a volume of the vessel. In mass, sum of all particles will be an integral of all electricity, all current in flow if we have applied voltage, sine voltage, voltage was something max, sine, where P capital, here we have 50 hertz, is 20 millisecond, it's at 50 hertz. Say we have, do we have it? You can go close. And the yellow line looks quite a sine. Integration of sine, or it's more preferable to introduce angular frequency omega being divided by repetition period, measurable in radians per second. So if we apply voltage changes by the sine law, yes, I'm moving. Hey, condenser current, come back. What do we see? Integration of sine x brings us cosine of x. Current changes by the inverse cosine law. It's like a time shift. This is a problem. Maybe it's something about condenser. I'll bring coiling. Let's try to switch a coil instead of inflate our condenser. Here is my coil. Put the coil. And rinse. adjust. Yes, a bit noisy, but 1 second, I'll bring the picture here. Two lamps, what we got? Oh, Kirchhoff is heavy. Now coil is inside, and what do we see? 0.8, 0.1, 0.83, but some only 1.2. Look at it. Look at that. Resistive load. Sum and two currents. Coil. Coil's current bit disturbed. Not an ideal coil. Look, the angular difference. Can you see? What's the difference? Currents by ampere net, reality. Again, I have coil. Shows if I have measurement, let's say, and some AC source. Current changes means what changes also induct induced flow to the coil winding. And when it changes, self-induction EMF emerges. Yeah, connect this. So, will be in, let's say, quantity of inductance by we will see first derivative. Thinking about voltage. Because flux When current changes, flux changes. And self-inductance EMF emerges, resisting what? Change of energy amount to attempting to prevent change of amount of energy stored in the coil magnetic field. So what shall we do with such network? It's one. We have problem. It's so Kirchhoff's law. Appears what Kirchhoff's law, not what. Solution to the problem we just solved was presented by Oliver Heaviside. Later, Charles Prater Steinmetz developed this technique to the, let's say, refined it. The idea of Heaviside was to use so-called symbolic or operator technique. Idea. We have voltage like sine omega. And let's say being something sine of omega t it's a simple trigonometry because we can replace. Actually, it's when we take y with x, it will give us cosine x, or the same sign but shifted by 90 degrees, something like this. So, what was the Heaviside idea with such values? There is one section or an area of mass dealing with complex number. There is, okay. The first idea is to introduce imaginary one, being a square root from -1. Think what can't exist, but let's imagine it's possible. If we imagine what square root from -1 exists somewhere, we can use a complex plane. This coordinate corresponds to our ordinary numbers. And imaginary one, the thing what cannot be. Some complex value, this point shows what it's a complex. We'll have a real part and imaginary part. Oh, let's say it's a B and A. So my number is A plus B. Real part, imaginary part. Here I have an end. 3. A will be length of the x multiplied by cosine of phi. And B will be the same length of x multiplied by sine of my angle phi. This one looks very similar to the voltage beam. We can think what this is. This vector on a complex plane in imagined space is something projected to, when projected to our world, gives us this voltage. So idea. For this one, real voltage we observe in reality is a projection to the imagined or imaginary part of some vector rotating with the speed of omega. If this is some current, we can assume it's, I don't know, let it be off, it also being projection of that some vector, and here is the alpha angle. It's projection of some delayed vector. So in this imaginable world, in the world of Heaviside, all electric values, all these AC quantities are projection of some vectors on the complex plane. One. Maybe this is voltage and this may be coil current and angular shift. They all rotate in theory with the speed of omega. Was one. Key moment. Since frequency is one and the same for all vectors, they all rotate synchronously, we can omit omega. There is no, until we have a different frequency in our schematic, or 2, 3, multiple frequencies. We can assume that complex plane stands still. Relations between vectors are independent on frequency here while this frequency is the same for all vectors, while they all real values are in synchronicity. Next step needed. Okay, they are vectors, but again, put x1 against OA as a function of time is an A. What to do with them? And Heaviside, the idea was to introduce a complex resistance. On a complex plane, we will receive a good representation of reality, assuming what reality is an image projection to the imaginary axis or imaginary part of the vector. So, coil current and condenser current should be vectors. Idea is to use a complex resistance. We, of course it's a Heaviside with Steinmetz, but okay, we are trying to implement Kirchhoff's and Ohm laws like it should be with the C network, or with some modification. So idea was to introduce an imaginary object complex resistance. To make this look like an Ohm law, what we need? First, integration gives us cosine with a minus sign. If this one is vector producing condenser voltage, we need a current. Cosine would be this way, minus cosine gives us something like this. So idea was to introduce a complex resistance. For capacitors it would be 1 against for coils. This is capacitance. For coils we would see something like this. UL EA. So introduction of XA being J omega N gives a very good picture. We just need to delay to P by 2. It means if we now assume what EA is OA divided by XA, everything will be okay, because we will divide by square root from -1, meaning rotation backwards by 90 degrees. One problem. Here is one problem. When you will integrate, you'll see difference. Corresponding to DC in where? In the values, everything, in the first look, working with instant values, everything will be okay, but later there will be problem with power. That's why one more step is needed. To make AC network represented as some imaginary complex plane to look like some kind of very strange but DC network, to use a known Kirchhoff and Ohm law, one step is needed. It is not necessary to calculate voltage and current. It is necessary when we speak on power. And it's idea of introducing so-called effective value. Idea, let's say we have DC source loaded with resistance. It produces P watts of heat. Okay. It's a DC EMF P. Oh. Or, okay, let's maybe DC. This amount, say it's P1, DC divided by R, and it will be current and multiplied by DC, so it's DC square divided by R. Very simple. Now let's see an AC equivalent. Idea. Same resistance. AC source with AC something loaded with same resistance and producing power P2. We may say that they are equivalent if P1 equals to P2. But these two sources are equivalent in power if powers are equal. Power produced by AC source within a period will be from 0 sum of all instant power, so AC square and 1 against that. It's a power within one period as being a sum of all instant power. Better say it's an energy. In fact, it's an energy within a period. Power in watts. What is 1 watt? 1 joule per 1 second will be 1 against by this law. Why? Simple. We divide energy produced within a time period by this time period to get energy flow in joules per second. So it can be written as 1 against R in from 0 to period OAC squared we started from equivalence. We want equivalence to. So, OBC squared divided by R is equivalent to 1 against inch 0 to OAC squared. And here equivalent DC voltage will be a square 1 against 0 OAC squared. This value, DC value equivalent to our AC. What kind of AC? 1 second. What was that voltage? Don't make a mistake. This one, amplitude. It's an amplitude. So, equivalent DC voltage producing the same power in watts, what what our AC voltage within a period. Per second, sorry. Watts is joule per second. It's called effective value or RMS root mean square value. To look like DC network calculation for our AC network calculation process, to look like AC network calculation, we need to use an effective or RMS values. For sine or cosine, integration gives no absolute no problem. So if you have voltage like sine omega, its RMS will be divided by square of 2. The same with the current. No problem. Take this integral and you get square root from 2. Now with the help of Heaviside's idea, what we will substitute? Let's see. DC, no. AC. We have a source. What we will use in our calculus? A with the amplitude divided by square. We have current source current source with amplitude divided by square root 2. Effective value. But this is for sine. Be careful. Resistance will be resistance. Coil with inductance A. Replace it with resistance J omega A. Okay. Capacitance of farads. Put an impedance 1 against J omega C. Easy. Schematics. Connection between nodes and branch. Now branch will consist of EMF. It may be complex, but anyway, greater or equal to 0 and smaller than infinity. And complex resistance with its module greater than 0 and smaller than infinity. We will represent schematics with the help of complex resistance. If, for example, I have resistance, coil and capacitance all here, for this branch will be plus J omega and plus 1 divided by complex resistance. But anyway, branch nodes, represent them with the matrix of M, the first incidence matrix. You need to do something with contours, no problem. If branch 4 is correspondence to the selected contour, walk on direction right plus 1. If goes in opposite, right minus 1, and everything will be okay. Resistance, no problem, just R matrix will become a complex thing. Anyway, branch, and fill it with the complex resistance of your branch according to the branch number. Voltage sources, no problem, just remember it will become complex. current sources, no problem, but remember, they can have imaginary part. Maybe you will face a problem of mutual couplet circuits. Let's say we have coil 1, coil 2, each has its own flux, but they also have a common flux or mutual flux. They are coupled. In such case, we speak about coupled network, magnetic coupling. Don't be afraid, just use elements of cell inductance. Let's say it's a branch number, and it's one number. Okay. No problem. Just A being equal to A being equal. You can account additional voltage drop from the inductance. Current in this coil induces voltage in the secondary coil. So if current flows here, we will see additional voltage drop here. And in opposite, current flowing here flows current, induces additional voltage drop in this network. Since magnetic coupling is symmetric, just add coupling element, add a position with our position. If this is, for example, 1 and this 2, we will have element 1, 2 and 2, 1 equal and equal to the J omega m, y J omega m, because it's induced the same way as it is with alternating flux, and everything will be okay. Nodal voltage method, nodal voltage equation will be the same with one small addition, imaginary part. So equation equals nodal voltage equation for DC network will become plus where Y nodal admittance matrix nodal admittance matrix calculated as inverse matrix of resistance, or if you prefer matrix of impedance, transpose first incidence matrix. The system by its nature remains a linear equation system. But now it will have complex coefficient, it will have complex three members vector, and it will produce a complex voltages. Voltages being by the idea vectors heaviside opens us a way of solution, assuming that these complex vectors are they are imaginary, but our real voltage, real currents, what we will observe, are projection to imaginary part of these imaginary vectors. So, it's the idea. Key element is to make a C network, look like very specific but DC network. You have to apply Kirchhoff and Ohm law by assuming what real values, what we observe, are projection of some vectors on a complex plane, and by introduction of complex resistance with imaginary part, to reflect a phase shift introduced by ability of capacitance and inductance to store energy. It's where the key element lies. So in the next part we will see how to implement this idea. In SciLab, I think we'll go with SciLab, but first we need to understand a simple idea of symbolic, it's called symbolic or heaviside technique, to assume what sine wave, voltage and currents are projection to the imaginary parts of some vectors, and what we can do? We can apply Kirchhoff and Ohm law to this complex values. And everything will be fine. Yeah. Answer to our if I draw a voltage like this, first current to active source will correspond. Capacitor current will go this way, and the sum will be something like this. Somewhere. If they are equal, this angle will be 3 by 4, 45 degrees, and its magnitude will be square root by no, currents are equal. I1 equals to I2. if currents are equal, magnitude will be not twice, if it should be with active, but square root from 2. That's where the difference comes. I think it's enough for today. Next time, let's see how to implement it.